Hello guys, welcome to the stream. We are 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 the fifth step tutorial. Today we're going to learn about the textures. Okay? Yes, what textures are and how to what do you call it? Build the textures in the OpenGL and how to map them. I'm just going to open my chat here. Sorry. Yes. And get the chat out here. Pop out chat. Okay. Okay. Yes. Can you guys see it? Both. Hello. Both screens. Code and the browser. I think so. Yes, we can start. What did we learn? We learned how to create the shaders. We learned how to use the shaders. We learned how to implement the shaders in separate files. I have written some code off stream yesterday. This is our vertex shader right now, fragment shader we're using, and this code is our shader class, which handles loading and unloading and using the shader code. Therefore, we have strings like the tutorial. I've implemented it like the tutorial. We're reading the files from the byte streams from the files and then casting it to the string streams, V stream and F stream respectively. And afterwards, we're setting them, we're reading them as string and passing them as an argument to the create shader and GL shader source functions methods, so to say. And these are for the error handling, and this creates the program. Yes, afterwards the programs attached to the shaders are attached to the program, and afterwards through the function use we can use this shader program. And I have also defined for various methods. These are used for, what do you call it, setting uniform variables. Yes, today I've done those things off stream, and today we're starting with the textures capital, and we're going to see what textures are, like I said, and how to use textures like this brick wall texture, and how to map textures like is it repeating, is it mirrored repeating, or is it clamped, or is it clamped to edge or to border. There are some what do you call it, texture wrapping modes. And we are also going to learn what texture filtering is. This is about the filtering of a texture, because we are getting a texture value for a pixel. We need to decide where exactly we want to return the texture value, because the texture elements are different than the picture elements. We're going to see if using the direct nearest neighbor or the bilinear filtering is better, and we're going to see the differences. And afterwards, we're seeing some meep maps, and what meep maps are, we're going to learn, and we're then going to create textures and load these textures, and we're going to generate textures. We're going to learn how to um, pass the texture data to the shader code, and we're in shaders we'll be then using the textures we've loaded, and we should then get some images with textures like this. And see. Yes. What can I say? I mean, here some more textures are implemented. I guess it's two textures. Yes, texture 2, as we can see in the code. We can, as we can see, import more textures up to 16. Okay, we're going to learn how many textures we can use for our primitives. Let's start. What are textures? Uh, yes, textures are assigning an image to assigning a 2D image to an object, I would say, to a primitive, I would say. And yes, let's read. What artists and programmers generally prefer is to use a texture. Of course, because setting colors for each primitive, each vertex is hard, as we saw yesterday. And the texture is a 2D image. Even 1D and 3D textures exist. A 1D texture is then called a color gradient, I guess, uh, where you can pick colors from a 1D line. And 3D textures should be like any other 3D object. It should has an image value in each vertex and each position of the object. So these are used to add details to objects, and yeah, we can imagine 2D textures on 3D objects to be folded down. Like if we have a roof object that happens to exist from two triangles. So I mean, you know what a roof is, and if we were to um, load and use an brick texture object, we would then take the 2D image and simply push it down on the roof, and this is how the texture mapping works, I guess. Let's see. Because we can insert a lot of detail in a single image, we can give the illusion the object is extremely detailed without having to specify extra vertices. So we can also manipulate manipulate the primitives, how the primitives look. See, this brick wall texture is mapped to our triangle. It normally seems like a solo color or an interpolated color, but this looks like it has more triangles than it seems, in my opinion. Um, yes, in order to map a texture to the triangle, we need to tell each vertex of the triangle which part of the texture it corresponds to. So each vertex gets a coordinate of the texture, and fragment interpolation then does the rest for the other fragments. The fragment will interpolates the other intermittent points. The texture coordinates range from 0 to 1 in the x and y axis. Yes, we use 2D texture images, so it doesn't have a z axis. Retrieving the texture color using texture coordinates is called sampling. Texture coordinates start at 0, 0 for the lower left of a corner texture image to 1, 1, sorry, for the upper right corner of a texture image. The following image shows how we map texture coordinates to the triangle. So we determine the left, we say that the left bottom vertex gets the 0.0 coordinate of the texture, and the right bottom vertex gets the 1.0, and so on so forth. And yes, we can add our text cards. I want to map I want to map a pizza to my shape. Pizza image. I'm going to take any JPG or any image, any pizza image that I can get. Only get it from the pizza, not I guess. See, can get this tar and a with. Okay. Can I be and pizza? Download. Don't want to download. Oh, this is PNG. I hope it's. Really. It's not. Whatever. We fine. We fine. We're going to make do. Okay. Now let's see. But how do we even set the how do we even determine the vertices in the textures? Okay, I can push it. I can use. I can do this. I can say this comes to the middle point, comes to the middle point of the image, which is 0.5, 0.5, and thereafter I could simply divide by 2 and edit, I guess. Edit or subtract it from the 0.5, 0.5. I guess this should work. Yes. So this doesn't make us implement it, but I'm just going to take some time here and determine my text coordinates. These are going to be then float text coords. Text coords equals an array, and I will like set 0.5, 0.5 for the first one, and the second one will then get 0.5 in the x coordinate and 0.9 in the y coordinate, and the third one will then get 0.7 f. You can 0.7 f, 0.8 f, and the fourth one will get 0.8 f, 0.75 f, a 0.9 f, to 0.5f, and the first 5 is ready. After that, we are going to type 0.8f and minus 0.25f and 0.3f and what f? What do I mean? Where am I? I have done this. Now I have to do this. 0.2 added 7f and select 0.3. This is 0.f. Add 0.7f and subtract 0.3. Good. 0.5f to 0.1f. Yes, these are the till this point written, and now I to subtract 2 0.3f and 3 0.2f and subtract 3 0.2f and subtract 2.5 0.2.5f and subtract 4 0.1f don't subtract 0.5f and subtract 3 0.2f at 2.5 0.75f much subtract 2 0.3f and add 0.3 0.8f. Yes, this should conclude 0.8f should conclude vertex text coordinates. Now we need to learn about texture wrapping. What is texture wrapping? Like we said, texture coordinates. What was that? Like we mentioned and set our coordinates, the texture coordinates range from usually range from 0 to 0 to 1 to 1. But what happens if we specify coordinates outside this range? What happens then? The default behavior of OpenGL is to repeat the texture images. We basically ignore integer part of the floating point texture coordinate. But there are more options OpenGL offers. The repeat is the repeating behavior. It ignores, like I said, the first digit and all the digits before the dot. And mirrored repeat puts the image, mirrors it, and mirrors it again, and repeats. Clamp to edge clamps the image to the edges, and I think in our texture, in our pizza texture, it would then create white and gray edges, and clamp to border simply clamps to a given user specified border color, so we can manipulate the color here, the borders. And the different output is shown here. Each of the aforementioned options can be set per coordinate axis ST and R. We are using 3D textures equivalent to X, Y, and Z with GL text parameter asterisk function, the GL texture wrap S, GL mirrored repeat, GL texture 2D. Okay, wrap S and do mirrored repeat, for example. But or like a GL text parameter FV, use GL texture 2D, use border color with this border color. First argument, he specifies the texture target. We are working with 2D texture, so the texture target is 2D texture. The second argument requires us to tell what option we want to set and for which texture axis. We want to configure it for both the S and T axis. The last argument requires us to pass in the texture wrapping mode we would like, and in this case OpenGL will set this texture wrapping option on the currently active texture with GL mirror repeat, because we are using GL mirror repeat. We chose the GL clamp to border option. We should also specify a border color, and the function changes a bit, and yeah, instead of getting an enum value, it gets a border color array float as a float array. And the texture filtering is like I mentioned, the nearest neighbor simply returns the pixel value that is nearest to the pixel. So in this case it returns simply this value, but in the linear mode you return an interpolation to the neighboring pixels. What does it mean? What does interpolation mean? Interpolation means between 4 pixels. Simply calculates the distance between the middle points of these pixels and interpolates between the first two of them, and it determines the color of the terms the returning color by simply determining the distance to the nearest 4 pixels, and simply calculating an interpolation between the 4 of them. So why is it called bilinear filtering? Because we are doing two linear filtering. We are first filtering this linearly between these two and these two, and afterwards while we have two lines and we know where our pixel is, we are then using this 2 lines and using the points and interpolating linearly once again. Therefore, because we are using we are filtering 2 times linearly, we call it bilinear filtering. And since it uses neighboring pixels and all of them, it creates more smooth images. GL linear produces a smoother pattern where the individual pixels are less visible, and it avoids this ladder-like behavior, I would say, this stairs-like behavior or pixelated look. What do you call it? Some developers prefer a more 8-bit look as a result, and as a result pick GL nearest option. If you want some pixelated color, pixelated output, you take the nearest one, and if you want more smooth and well, I would say better looking to human images, you take linear. And how do we set it? With the text parameter function, as always. This yes, this is different. We can set it we can set 2 different parameters to 2 different operations if the object is too, how do you call, too distant from the camera. It will then minify it, and if it's too near to the camera it will magnify it. So we can set different filters uh, to be used while magnifying it or minifying it accordingly. And these are both set with the GL text parameter functions and the arguments GL texture min filter and GL texture mag filter. MIP maps. What are MIP maps? Let's see. MIP maps is a concept to make the texture smaller than it actually is. It uses for example, the 4 pixels here and the left top area and the most left top area, and calculates the average color of these 4 pixels and simply writes it as a 1 pixel in the next level, and so forth, so forth. It creates more textures. This is like the MIP map level 1, the where the size is simply divided by 4, and this is MIP map level 2. This is divided by 16, 32, not 32, 64, and vice versa. Yes, this is 1/4, this is 1/16, 1/64. Yes. Like this simply explains what I understand. Switching between map levels. You can simply say you're taking this one and this one because the pixel footprint is like in between. You simply say you have to interpolate between these two MIP maps, and therefore you can. Let me just read it. Maybe it explains another thing. And switching between MIP map levels during rendering OpenGL may show the MIP map levels are generated through this call. And when switching between MIP maps levels during rendering, OpenGL may show some artifacts like sharp edges visible between the two MIP map layers. Just like normal texture filtering, it's also possible to filter between MIP map levels using nearest and linear filtering for switching between MIP map levels. Okay. To specify the filtering method between MIP map levels, we can replace the original filtering methods with one of the following 4 options. What are these options? Nearest MIP map nearest. Takes the nearest MIP map to match the pixel size and uses the nearest neighbor interpolation for texture sampling. Takes the nearest MIP map level and samples that using linear interpolation. Linearly interpolates between two MIP maps. This is what I said. If the pixel footprint is somewhat in between, it doesn't take the nearest MIP map level, but it takes the interpolation between them, the color interpolation between them, and then it takes the nearest neighbor of the interpolated level, and the last one is interpolation times 2. And how are these set? We had GL nearest or GL linear. Now we can set GL linear, MIP map linear, or GL linear, I don't know what. And MIP maps are used for minimums, minifying, and MIP maps are not used for magnifying. Magnifying should be like the um, what you call it, the detective gadget thingy. How do we load images, textures? Therefore, we define a header file. Let's see what it does. First thing we need to actually use the textures is to load them into our application. Okay, texture images can be stored in dozens of file formats, each with their own structure and ordering of data. So how do we get those images in our application? And one solution would be to choose a file format, like say we would like to use say .png and write our own image loader to convert the image format into a large array of bytes. While it's not very hard to write your own image loader, it's still cumbersome. And what if you want to support more file formats? You then have to write an image loader for each format you want to support. True, there should be a library or a function to load the images in the program. Another solution, and probably a good one, is to use an image loading library. There is a library and that supports several popular formats and does all the work for us. A library like stbimage.h. How do we download it? We can download it there. stb.image.h on stbimage.h, please. Where is it? Let's try again. Cut it and get it to the graphics programming um, and libraries and include file, and simply dump it in the util where is it, util folder. Okay, and create an additional C++ file with the following code. Why do we do it? Sorry, but why are we creating a C++ file? Following thing. Either this side. Uh, uh, function images, color channels. Okay. Sure. And I'm guessing that we create a texture here with the GLGen textures method, but this texture should then be first non-existent, white or black image. Then I think we will bind our image to the texture. Let's see. Function first takes as input how many textures you want to generate and stores them in an unsigned int array given as its second argument. In our case, just a single unsigned integer. Just like other objects, we need to bind it so any subsequent texture commands will configure the currently bound texture. Then we're binding a 2D texture to our texture. Now that our texture is bound, start generating a texture loaded. This is created and generated by using GL text image. This takes target. Target is a 2D texture. Level, mipmap level. It takes a mipmap level, I guess. Yes, the second argument specifies the mipmap level for which we want to create a texture. If you want to set each mipmap level manually, but you'll leave it at the base level, which is 0. Here, here's format. We're setting the width, height of the texture, and don't want border is always null. And the next one, 7th and 8th arguments specify the format and the data type of the source image. We loaded the image with RGB values and stored them as chars. Okay, therefore we are using our array. Okay. So type one more GLRGB and L unsigned byte. And at last we are typing our data in. Typing in the data. Okay. We loaded our 2D texture. We are creating its mipmap. Generate mipmap. Or a 2D texture. Yes. If we understood the parameters, I'm getting that. Passing those. GL text image 2D is called. The bound texture object now has a texture image attached to it. However, currently it has the base level of the texture image, so we call generate bitmap. That is straightforward. And after we are done generating the texture and its corresponding bitmaps, it's good to practice to free. It's good practice to free the image memory. So we're just calling stbi calling the library and the function of library. Simply pass on our data is read. The whole process of generating a texture does look something like this. It controls here, by the way, if the data is existent by simply checking if it's not an empty array. We could do that, but we could also simply say that here right now we could simply write if not data. We could simply push some string to the output. Failed texture load and end line. Yes, this should also work. And afterwards it's freed. Yes. How do we apply textures? We have seen we need to set the coordinates for the textures, how to map the coordinates to the primitives. We have already done it in our vertex in this ports array. But I'm thinking though if I should merge these arrays or simply and add another, but I think it's good practice to merge the array. I am going to add 2 more inputs for each vertex. Here, not like this. Okay. Simply, or I or texture coordinate. Position. X, Y, Z. R, G, texture coordinate. Um, of course, we have changed. We need to change our vertex and fragment shaders afterwards. What's this vertex entry pointer to? It adds another it adds another. I can bulk. Where was I? Here it is. This is for the vertex attribute pointer 1. Is in vertex shader, so we can simply the vertex shader again, location st, can simply say gl vertex attribute pointer to load. It's normalized, so I don't need to normalize it, and the stride. It was 6 before, it's now 8 size of load, and we have to cast it to avoid. Should start after 6 times. After 6 times load. Size of load. Change the right here to 8. Sorry, because the array has changed. Now we should enable another vertex attribute array. We'll enable vertex attribute array 2. It takes it a text coord here. It outputs directly to the fragment shader. So we say out vec2 text coord. So the text coord equals st simply, and this here vec2 text coord afterward uses this text coord. Anyhow, there is a sampler here, uniform sampler 2D. The fragment shader should then accept the text coord output variable as an input variable. The fragment shader should also have access to the texture object, but how do we pass the texture object to the fragment shader? I mean, yes, how do we set it? How we know what the coordinates are, but how do we set the text? DGRSL has a built-in data type for texture objects called a sampler that takes as a postfix the texture type. We want a sampler 1D, sampler 3D, or defined as an form, as a uniform sampler D text. What determines the fragment color by simply calling a texture method with sampler as the first argument, the coordinate second argument. Bind a uniform variable here, which would be done here. No? Before calling draw element. Before calling. Okay, my bad. My bad indeed. Yes. To call it after created texture. I guess so. I'm just typing BL not bound, but it's created now. Okay, okay, we bound. Oh, oh, if the texture is bound, it means okay, bounds. It binds it already if template. Okay, let's see. Will texture load? Why though? And my own code. My own code. Never. Think I will simply take the map here. That I mean. Bam. Bam. Should work. It load the texture. Okay, it loads the texture. I can see something. I can see something. If I click F here, it should work. Hopefully. Surely it will work. Let's press together. Oh, the best margarita pizza in the world. Or what? Oh, it's pepperoni. What am I saying? What am I even saying? But the description of the texture calls it margarita. This is so funny. This margarita pizza is funny, guys. What happens if I make the viewport larger? It also large. What if I make cursed pizza? Cursed pizza. Close. That's Turkish pide, huh? Yeah. Yes, our first pizza is rendered. Let's see. Let's change this pizza. The wine turbine. Wines. What wind turbine texture. Turbine. P. documents and folder here called textures. And simply say textures, change the Veronipit and that. Simple as that. Can't. There. Should be 4 here. Oh yes, it's the RGBA. So yes, the fan is ready. But this is simply, I don't know. It's look, it's fine, it's fine. We have displayed our textures. Not a very happens if I change it. So the RGBA. So I call it P. Okay, change it again. Says 3 all of a sudden, and it doesn't display. So the pizza doesn't have 4 channels. It has 3 channels. It doesn't have alpha channel, but the fan has alpha channel, so it doesn't display it. Yes. Now we're going to use the fragment color, alter the fragment color using the texture and our color. Therefore, I'm going to the fragment shader and simply adding the same code with this guy multiplied by like 4 created by color, simply type color, and it should look a bluish fan, like a bluish fan. Yes, it does indeed look like a bluish fan. Yes. Now we're talking. This more looks like our shape. Yes, texture units. Where are we in the step? We have a little bit more. Okay, we're nearly ready. We're nearly done. You probably wondered why the sampler 2D variable is a uniform if we didn't even assign it some value with GL uniform. Okay, I really wondered this, by the way. Wondered about this. Using GL uniform 1e, we can actually assign a location value to the texture sample, so we can set multiple textures at once in a fragment shader. This is really nice. This location of a texture is more commonly known as a texture unit. The default texture unit for a texture is null, which 0, which is the default active texture unit, so we don't need to assign a location in the previous section. Note that not all the graphics drivers assign a default texture unit, so the previous section may not have rendered for you. Okay, that's weird. The main purpose of texture units is to allow us to use more than one texture in our shaders, and by assigning texture units to the samplers, we can bind to multiple textures at once, as long as we activate the corresponding texture unit first. Just like GL bind textures, we can activate texture units using GL activate texture, passing in the texture unit we would like to use. Okay, GL texture 0 is then activated by the texture. All right. GL gen textures, GL bind texture, GL text image 2D. After activating a texture unit, a subsequent GL bind texture call will bind that texture to the currently active texture unit. Texture unit GL texture 0 is always by default activated, so we don't have to activate any texture units in the previous example when using GL bind texture. So I will simply add the pizza texture here again by calling it after this GL activate texture, GL texture 1 texture. It is undefined. Active texture, not activate. And then GL bind texture. GL bind. Oh, you can see. Sorry. GL bind texture. We bind GL texture 2D, and with our texture. Texture. And what is our texture? Like this. Texture array of 2. Texture. Generate textures. Texture first. And this. Bind texture to texture 2. And get text image 2D. really text image 2D, GL texture 2D, texture 2D 0 times RGB because the pizza image doesn't have any alpha color. Width and height is overwritten. Overwritten by calling stbi load data equals stbi load. Same here. Same argument here, but times its pizza. Yes, afterwards I am going to call it 0 glRGB and this format. This is an unsigned byte. See, hate this camera position. Signed byte data. Yes. It reads the image. It then creates the generate. It then creates bitmap. Texture for the pizza. And yes. Yes. It's all. The second texture is generated. We could simply then add another sampler here. It's uniform sampler 2D. This time it's pizza text. First one now Fantex. And here it uses a mix. Mix texture 1, texture 2, 0.2. A value of 0.2 will return 80% of the first input color and 20% of the second input color, resulting in a mixture of both of our textures. Well, how does it load it? Simply the same. Awesome face, width, height, whatever. It actives, it sets it as active. It binds it to texture 1. Wait, what? It writes to texture 1 and texture 2. This is created via GL create function. It draws elements, it binds vertex array, whatever. We also have to tell OpenGL to which texture unit each shader sampler belongs to by setting each sampler using GL. Why are we using this, by the way? We're setting fan text to 0 and setting pizza text to 1. By setting the samplers via GAdd uniform 1 for each uniform sample to follow. You probably notice that the text is flipped upside down. It happens because OpenGL expects the 0.0 coordinate on the y-axis to be on the bottom side of the image, but the image flip vertically. Okay. So I should mix them, my fragment code, and don't use color anymore. I will use it anyway. Mix the texture fun with the texture 2, texture fan text, text chord, and using 0.7f, and also multiplying with the color. Feel it? Whoa! This guy's a fan. I can decide. The pizza fan. Call it fan. Fan. Yes, guys, we have created the first pizza fan of the world. Both a pizza and a fan. So we have completed this step of the tutorial. I will make exercises after I'm done with the chapter. That means I will simply complete all these sections of the first chapter getting started, and I will then continue with the exercises so that I can review what I have learned. The next lecture next section we're going to work on will be transformations. This is a more of a theoretical section. It has some mathematical functions, mathematical lectures, matrix vector, and so forth. And afterwards comes the coordinates. And last 3 sections actually after to get started to the OpenGL, and then we're going to do some stuff, the boring stuff, the boilerplate code writing stuff, the stuff everyone needs to know to get started to OpenGL. But once they're done, we're coming to good stuff like Lightning. Afterwards, we can start a project. Actually, I will actually design a project after completing the getting started chapter. So I will come up with a game idea and try to find the assets, try to find the required classes, required characters, required, I don't know, inventory items, and then I will model the game in a diagram. I will create the interactions, the assets, items, between the characters, between the, I don't know, minions, and afterwards I will learn the chapters one by one, and I will try to um, match them, map them with my project, and so the project will progress with my learning. So that's it for today. I know last 3 to 4 days I'm holding the streams a bit short, but yes. See you later, I hope, on Friday, and if not, on Saturday. Have a nice day and see you later, everyone.